Look up at the stars at night and they twinkle. It looks romantic, but to astronomers, that twinkling is a total nightmare. Here's why. Stars don't actually flicker. That shimmer you see is starlight getting bounced around on its way through our atmosphere. Earth's atmosphere is like a thick, wavy swimming pool of hot air, water vapor, and gas that distorts incoming light rays. Pockets of air at different temperatures bend light in slightly different directions every fraction of a second. For a casual stargazer, that's a beautiful effect. For a scientist trying to photograph a galaxy 10 billion light years away, it's a blurry mess. Even the best ground-based telescopes perched on remote mountain tops above the thickest air still fight this problem every single night. So to see the edge of the visible universe in sharp, unblurred detail, scientists had to do something crazy: skip the atmosphere entirely. That meant launching multi-billion-dollar delicate giant mirrors on top of a rocket and putting them into the vacuum of space, hundreds or even a million miles from Earth. No air, no clouds, no twinkling, just pure, undisturbed light traveling in a straight line for billions of years, finally reaching a mirror built to catch it. That's exactly what Hubble and James Webb were built to do. Let's look at how. Space telescopes aren't long glass tubes with lenses, like the little refractor you might have gotten as a kid. They're reflecting telescopes, and instead of bending light through glass, they bounce it off curved mirrors. Here's the basic path. Light travels for millions or billions of years, hits a large curved primary mirror at the back of the telescope, and reflects forward onto a smaller secondary mirror. That secondary mirror then bounces the light again straight into a bay of sensors, where it finally gets turned into an image. Two bounces and an ancient beam of starlight becomes a picture on your screen. Now, think of the primary mirror as a light bucket. The wider the bucket, the more photons it can catch from faint, distant galaxies that are barely emitting any light at all by the time it reaches us. That's why the size of the mirror matters so much. Hubble's primary mirror is 2.4 meters wide, a little over the height of an NBA player lying down. It was a revolutionary size for its time. James Webb blew right past it. Its primary mirror is 6.5 meters wide, made of 18 separate hexagonal segments that unfold in space like a flower opening and lock into place with mirror precision. That's roughly 7 times the light collecting area of Hubble, which means Webb can spot galaxies that are fainter, older, and farther away than anything Hubble could ever detect. So why gold? James Webb's 18 beryllium segments are coated in a layer of gold 1,000 times thinner than a human hair. Gold might sound like showing off, but it's actually chosen for physics, not looks. Gold is one of the best materials known for reflecting infrared light, and infrared is exactly the kind of light Webb was built to see. As light from the earliest galaxies travels across the universe, it gets stretched into infrared wavelengths, invisible to our eyes but perfectly visible to gold-coated mirrors tuned to catch it. Beryllium was chosen for the mirror segments themselves because it's incredibly lightweight, yet stays rigid even at the punishing cold temperatures of deep space, where most metals would warp or crack. So in short, bigger mirrors mean more light, and the right coating means the right kind of light. Together, that's how these telescopes reach across billions of years of cosmic history. Once light finally reaches the sensors, the real magic happens. CCD detectors, short for charge-coupled devices, count individual photons as they land one by one and convert that count into binary code, ones and zeros. That digital signal gets compressed, packaged, and beamed back to Earth over radio waves, crossing hundreds of thousands or even 1,000,000 miles of space before landing in a control room, where scientists turn it back into the images you see online. But infrared telescopes like James Webb face a deadly enemy: heat. Every object gives off some infrared radiation just by existing, including the telescope itself. If Webb's own mirrors and instruments warmed up even slightly, the telescope's own body would glow in infrared and completely drown out the faint infrared light coming from distant galaxies. It would be like trying to spot a candle flame while standing next to a bonfire. So engineers had to solve an extreme cooling problem. Webb needed to operate at around minus 370 degrees Fahrenheit or minus 223 degrees Celsius, colder than almost anywhere naturally found on Earth. And it needed to stay that cold constantly without any way to plug in a refrigerator a million miles from home. The solution was a 5-layer sunshield, roughly the size of a tennis court, unfolding in deep space like a giant metallic kite. Each layer is a thin, specially coated membrane, and each layer blocks and redirects heat from the sun before it ever reaches the telescope's optics. By the time sunlight fights through all 5 layers, its heat has dropped by a factor of about 1 million. The side facing the sun bakes at over 230 degrees Fahrenheit, while the shaded side, where the mirrors and sensors sit, stays deep in the cold of space. That sunshield had to unfold perfectly, with over 100 single-point failures, meaning if even one mechanism jammed, the whole mission could have been lost. It worked. And because of it, Webb's infrared eyes stay cold enough and quiet enough to detect light from some of the very first galaxies that ever formed. Here's a problem you might not expect. Rockets are narrow, and telescope mirrors are enormous. Webb's 21-foot mirror simply could not fit inside any rocket fairing fully assembled, so engineers turned the entire telescope into a giant piece of space origami. The mirror segments folded inward, the sunshield compressed down into a tight stack of thin membranes, and the whole structure was squeezed into the nose cone of an Ariane 5 rocket, launched from French Guiana. Once Webb reached space, it had to unfold itself piece by piece with no astronauts nearby to help and no chance for repairs if something went wrong. Mirror segments swung into place. The sunshield unfurled to the size of a tennis court. It was, without exaggeration, one of the most complex deployments ever attempted in the history of spaceflight, and it worked flawlessly. From Hubble revealing the deep, star-filled universe for the first time, to James Webb uncovering galaxies that formed just a few 100 million years after the Big Bang, these floating eyes keep rewriting what we know about our own existence. And this isn't the end. Future telescopes are already being designed to look even further back, closer to the beginning of time itself. If this kind of thing fascinates you as much as it fascinates me, subscribe, and I'll see you in the next one.